Professor Mohit Bansal. He's the John and Louis Parker Distinguished Professor and Director of the Multimodal Understanding, Reasoning, and Generation Lab at UNC Chapel Hill. He obtained his PhD in 2013 at UC Berkeley, and he's particularly focused. He comes from an NLP background, and he's focused on multimodal learning, especially generation, semantics, and interpretability. He's been a recipient of many awards from prestigious organizations such as DARPA, NSF, Google, Microsoft, the Army Research Lab, and so on. He's previously won outstanding paper awards at the Association for Computing Linguistics, CVPR, EACL, Coling, and CoNLL. And he's also been a keynote speaker at these top conferences. Today, he's going to give a talk on generative video LLMs, planning agents, and multimodal composition. Yeah, thanks. It's over to Dr. Bansal.
Great. Yeah. Thanks for the introduction. And I'm sad I couldn't make it there in person. I was almost able to, but then there's a last minute childcare clash. But hoping to see you all at the next event. So I have around maybe 28 minutes. So let me get started. I'll basically cover two aspects of generative video models today. One is how can we incorporate planning agents into them for consistent and efficient sort of long video generation, as well as all the way to refinement. And then the second part will be on multimodal composition, where the goal will be just to give you a little bit more detail, right? The goal is for planning agents, we want to be able to do controllable image and long video generation, all the way to things like infinite story simulation, motion retrieval for video generation, as well as the whole closing the loop, right, of the whole pipeline for finding the errors through planning in the generated videos and then correcting only the targeted incorrect parts. And then the second part will be about multimodal composition, more specifically things like any-to-any generation, right? Can we take any subset of input modalities and be able to generate any subset of output modalities, including multimodal compositional information inside generated videos, as well as any-to-any control and 3D camera control. So just to give you a little bit of a brief background, right? So why sort of we are motivating planning agents here, right? So if you start from text to image kind of motivation, right? A lot of this is through black box models even today, right? So if I have some simple prompts like two Pikachus on a table or a truck is behind a motorcycle, right? Things like counting or spatial relations, right? And these are obviously more simple prompts, right? But real world long prompts have even more right, complex planning and relationship scenarios. So we will notice some good visual quality, but very quickly we will notice a lot of important semantic issues, right, where there's a lack of fine-grained layout or planning control, and then interpretability behind the process, as well as right lack of faithfulness to the input prompt, both in terms of positive or negative hallucinations, but also out of domain generalization. So in NeurIPS 2023, we proposed this visual programming kind of paradigm for step-by-step text-to-image generation. And this is a very high-level overview of the motivation where if the prompt comes in, right, we first ask a planning agent, which could be an LLM, right, to first count all the objects and their numbers, right, their counts in the prompt. And then taking those objects and their counts, can we use the LLM sort of prepositional and other relationship and other kinds of knowledge to be able to also plan the bounding boxes, right? The layouts, the coordinates of the layout for these different objects. For example, if it's two Pikachus on a table, then learning that the average Y coordinate for the Pikachu boxes should be higher than the average Y coordinate of the table box, versus if it said two Pikachus under a table, right, then it should generate the reverse spatial relationships in the bounding boxes. And then finally doing right in painting to get the final image. So I'll not focus too much on this since I want to focus on the video parts of these ideas, but just as a brief sort of motivation, you'll see in the NeurIPS 2023 paper that we basically had metrics focusing on things like counting, spatial relationships, and scale. Right, three boards or a truck is behind a motorcycle, or scale would be something like a remote is bigger than a cat. And we can see here that we are able to get much larger improvements because of the fact that we're not directly generating the image, but first we are making sure that the faithfulness to the count or the spatial relationship or the scale relationship is true, right, based on the bounding boxes and their positions, right? So we're already generating the bounding box for the motorcycle in front of the truck, right? Such that the truck is behind the motorcycle, and so on. So the goal here was that it's not just allowing you to have more explicit control over these properties, but in fact, you could even go in, right, as human in the loop and change the boxes if you still don't like them or you want to change them, right? As well as handle more sort of unseen scenarios. For example, a remote is bigger than a cat. And more importantly, it's not just letting you understand the process behind the image or video generation, but also the model itself, right? Because there's a lot of studies now showing that generative models themselves, right, cannot really understand or do understanding tasks or reasoning tasks on their own generations. But let me go into the sort of newer video version of this, right? So this is also one of the first sort of long video generation models based on planning agents, right? So this was, I think, from around fall 2023, and then published at Column 2024, where the idea was that can we first have a video planner stage where given, I'll show you more complex examples later, but if you have this simple example like a hungry cat is finding food, then the video planning stage, right, would use an LLM to be able to first decide what are the different subscenes in generating this long video. So maybe the first scene it will come up with is a cat is lying down on a bed. It will also generate the frames of the first scene and their bounding boxes, right? So basically, it will decide that there's an orange entity, right, the orange box for the cat, and where is it located, and then it'll also generate a green entity for the bed, and then the background it'll decide is the bedroom. Then it will decide that the next scene could be about the cat getting up, and that will change the bounding boxes, right? So if the cat is getting up, then the shape of the bounding box, right, becomes taller as opposed to right, more horizontally wide, and then the bed sort of stays the same, the background stays the same, and then the third scene could be that the kitchen right comes in as the background, and so the cat has to then go to the kitchen and eat a snack because it's the stories about a hungry cat finding food. And here it decides to bring in a new entity, right, which is the snack. So the color coding is basically think of it as something like co-reference resolution, right? It's actually deciding which entities sort of belong to the same, which bounding boxes, right, mentions belong to the same entity. So it color codes the same, and as you'll see in the second stage, which is the video generation stage, which we call layout to vid, it will also share parameters, right, representations across the bounding boxes of the same entity, right, so that they can be temporally consistent. So in the second stage video generation, it takes all the different scene descriptions as well as all these layout plans, right, for the different sub scenes of the long video, and also the color coded consistency groupings. And then what we do is we basically take the spatial temporal blocks of a single scene video generation model, and we go inside the spatial attention block and we insert these guided 2D attention modules, which basically allow us to insert the layout conditions and the scene text, right, in a very targeted way. And the best part is that only these guided 2D attention modules are updated, which is only 10% of the parameters. And we also share parameters across the boxes with the same color, right? And we actually use both image and text joint representations for consistency, which we showed that works better than just textual or visual representations. So end of the day, all of this allows us to actually train the whole sort of model with only around 8 A6000s or 4 A100s, right, in a very efficient way. So here are some output examples from the video director GPT model, where it's these are some examples of basic physics like gravity, right? If the prompt is a stone thrown into the sky, a cat is approaching from a distance, right? So the zoom in versus zoom out perspective. It's also generating things with some notion of static versus dynamic objects in mind, right? So if the movement of the camera is for a static object like a bottle on a table, then the bottle shouldn't move, only the camera should move. Whereas for things like airplanes, both the object and the camera, right, have independent movements. And then in terms of real sort of long video generation, here is one scenario where we can give it multiple sentences, right? The full multi-sentence story. A mouse is holding a book, makes a happy face, happy and talks, pulls petals of the flower, holding the petal by his right paw. So you can see that this is holding by the right paw, right? And then in the beginning, you also saw that it was reading a book here, right? So now it's looping back. So this is basically showing you two things, right? That this is almost from 2 years ago, right? So this was the first approach for long video consistency, where we are doing two main sort of contributions here. One is very fine-grained, right, sort of low-level control of out-of-domain scenarios, like, right, a mouse holding a book and holding the petal by the right flower, the right paw. But also the important part was being able to have consistency, right, of the characters across the longer video, while being able to do all of this right in only 4 800s kind of capacity. Now, this is also another scenario where instead of giving it the full story, you could actually give it a single sentence, just the high level story of make a strawberry surprise, and then it can first automatically generate all the sub scenes and the sub scene frames for the story, right, in a consistent way, and then generate the final long video. Another interesting thing, which is pretty important, right, is that instead of us trying to get lucky with trying the prompts again and again or trying to re-engineer the prompt, right, these models allow you to have human in the loop, right, fine-grained editing and control, where if you generate an output video and you don't like some aspects of it, right, instead of trying to just get lucky with a new prompt, right, with small changes in the prompt, you can actually go in and make the horse smaller or change the background, right, label of the bounding box for grassland versus Night Street and so on. So then next at iClear 2025, we have sort of a longer next step version of this called Unbounded in collaboration with Google, called a generative infinite game of character life simulation. So the idea here is that you basically can have a user defined character. For example, in this case, it's Archibus, which is a user's custom wizard character. And then the user can actually have natural language based flexible conversation, right, interaction with this generative game. So you will have these different axes or meters, right? Like in a game, like hunger meter and energy meter and fun meter, right? As you can see on the sort of left corner here. I don't know if you can see I guess my mouse pointer doesn't work on the screen for some reason. But you see that in the left, right bottom corner of the game screen. So basically a spontaneous and unconstrained story can unfold here while the user is playing, and the character can explore these new environments, right? So we can have a different kind of myriad of possible actions and unexpected explorations. And it's also very interactive, right? Refreshing every second. So here you will see like the user will first say, I tell Archibus to go to the flowery meadows and forage for pears. Uh, and then, just to check, do you see my mouse pointer or no?
Yeah, we can see it, I think.
Okay. And you see my full screen, right? Not like the presenter view or something.
Yeah, we see the full screen.
Okay. Yeah, so basically, right, for example, Archibus the wizard in the first part of the game, right, gives feedback to his students pointing to their strengths and areas for improvement, and then he's getting hungry. So then the user can say, I tell Archibus to go to the flowery meadows and forage for pears. So now in the second scene, you will see he has come to the meadows, and so, right, Archibus is eating the plate of pears, sitting on the flowery meadows. He's content and full, but feels slightly bored. So then the user can come in and say, Archibus, let's head back to the classroom to study magic. And then, right, the scene changes to the classroom again, and then Archibus, right, is back to the classroom, opens up a dusty book, causing the room to hum with arcane energy. Right, what next? Archibus, let's go to sleep. It's getting late. So this is sort of like a way to be involved inside the game, right, through natural language interaction, while creating a consistent long video where you're also interacting with the video, right, as a game, as opposed to just generating the video as a static process. So that's sort of the main idea here. I'll not again go into too much of the method details. There's a lot of technical innovations that you can see in the paper, but the basic process is, like I said, the game setup comes with user instructions and character actions. And then step one is, right, you take the user input character and game topic, right? For example, a young witch and a dragon hunting topic, then it will automatically generate the different game environments like forests, ponds, villages, and mountains. And then you will start this multi-branching process, right, of story unfolding, where if the first branch is about hunting the dragon, then it will try to generate things like, fighting with magic, the dragon is retreating, right? Then you rest and eat, and then you go to the pond, as opposed to if the story branch is about buying potion, then it's more about going to the village, right, going to the shopping place, then buying potion, having food. So it has basically this sort of infinite branching of different parts of the story as it unfolds. And here are some examples of different characters, right, in different scenarios with different sort of energy hunger meters. Now, in terms of the next steps, right, for having planning agents be able to help video generation models, I want to talk about something called DreamRunner, which is about fine-grained compositional story to video generation with retrieval augmented motion. So the idea here is that a lot of you have, right, obviously you worked with and heard of RAGs, right, retrieval augmented generation has been very successful for right, the language and text generation side. So in this case, what we want to do is we want to be able to use the same kind of power of retrieval, but for very complex and unseen motions and object combinations for video generation. So the idea here for DreamRunner is that this right plan generation stage, which you see in the middle here, right? So the prompt comes in. It will first generate a hierarchical plan where the high level plan is about different scenes, motions, and narrations, right? Scene one, motion one, narration one, versus scene two could be about study room. Motion will be about writing, sipping, and sitting. And then there's a narration. And then the fine grained plan goes more into this detailed sort of right layout bounding box kind of setup where it's deciding the exact layout of right that frame. So this is sort of the first stage. And then the second stage has two parts. 2.1 is motion retrieval and prior learning, right? So the idea here is that given the motion that's needed in this input prompt, we will go and retrieve the most relevant videos from a video database that has those desired motions. So for example, if it's a witch sipping tea, we will retrieve videos of right humans sipping tea, and we will then go and learn this motion prior through test time fine tuning. So we will take those retrieve videos and we will do test time fine tuning to convert it to extracting the just the motion prior from those videos. And then the same thing we'll do for objects, right, which we call stage 2.2, which is subject prior learning, where we can either take the user's reference images, right, their favorite pet cats or their products, right, and or we can also retrieve it if they don't want to provide an image. And then we will again convert this to test time fine tuning into just the character priors. And then the final stage three basically takes these character priors and these motion priors, right? And it basically does this thing called SR3AI, where we equip a diffusion model with these novel spatial temporal region-based 3D attention and prior injection modules, such that it can take these character priors and motion priors and then be able to right mix them into this very sort of fine-grained controlled video generation, where you can see this video playing now where right the cat is there with the witch sipping tea in the meadows. And then finally, I want to close the loop here for planning agents for video generation, where as I showed you, right, there's a human in the loop control where if you have segmentation masks or bounding boxes, right, in the generated video, we could have a human, right, come in the loop and decide the errors in the generated video and then fix them, right, manually. But what if we want to automate this process, right? So this is what video repair does, which is called improving text to video generation via misalignment evaluation and localized refinement. And the main goal here is that once the video is generated, can we use automatic metrics to decide which parts of the video were generated correctly versus incorrectly, and then only refine the incorrect parts of the generated video, as opposed to again trying thousands of different prompts, right, and trying to get lucky that okay, like let me just try again and generate the whole thing from scratch, because then maybe something that was incorrect became correct, but then right the correct thing became incorrect. So that this is what video repair does. It has three stages: video object evaluation, video refinement planning, and localized refinement. So the initial generated video comes in, right? Suppose the prompt was one bear and two people making pizza. Then what we'll do is we'll go into this metric called DSG, Davidsonian Scene Graph. So we had this work at last iClear 2024 called Davidsonian Scene Graph with Google, where the idea is can we convert the prompt to a set of semantic questions such that every question has a unique point and covers the whole prompt jointly, as well as there's valid dependencies that if the motorcycle is not present, then I will not ask questions about the color or the size of the motorcycle or the location, right? So we convert this image-based DSG metric and extend it to videos. And the idea here is that once you get the evaluation results of which parts of the generated video were correct or incorrect, you take the correct parts and you decide the preserving object regions. So basically the green stuff is showing the preservation part where you are keep deciding based on the correct parts of the generated video what regions to preserve, right, using segmentation masking. And what parts of the evaluation came out to be incorrect tells you what needs to be refined, right? So in this case, if it was one bear and two people making pizza, the evaluation tells us that one bear and one person was already generated correctly. So let's preserve that. And let's refine the rest of the region, as well as it generates a refined prompt which is only about the rest of the correction, right? So now it only needs one person making pizza, and this all goes into the third stage where you get the region to preserve, right, with the initial noise and initial prompt plus the region to refine, which is right the gray part here, and it has a resampled noise function as well as the refined prompt. And then both of these get combined to generate the refined corrected video, which has the two people and one bear making pizza. So that's sort of the main goal here. Now, in the second part of the talk, which I'll keep around 10 minutes for, is called a multimodal composition. Like I said, for being able to do interactive and generalizable any to any generation. So the first aspect here that I'll go into is called Cody. This was a collaboration with Microsoft at NeurIPS 2023, which was sort of the first approach to show how you can take any unseen combination of input modalities and be able to generate any other unseen combination of output modalities while having a linear number of training objectives and also not depending on training data for all kinds of combinations. So let me show you a brief demo here, and hopefully the sound is audible. So basically, sorry, can someone verify if the sound is audible?
Yeah, we can hear it.
Great. Yeah, so I can do something simple. Like suppose you have a storyboard, right? You have a folder of images, you might have some texts, and then you also might have audio clips. So I can tell Cody, which is composable diffusion for any to any generation, to first take in maybe the audio track and then generate some text for it, right? Or I could do something more complex saying, hey, take both these inputs, the image and the audio clip, and generate a new audio clip. So I don't know if you can hear it now, but the audio clip now changes to not just rain, but rain plus street sound, because the street image, right? Its latent LDM latent variable is mixed with the audio for the rain. So now it generates rain plus street sound. Or I can ask it to do something more complex, like take all these three inputs, the text, the image, and the audio clip, and maybe generate a new image, as well as its description, right? So now you will see that it's respecting the text prompt for the teddy bear on the skateboard, while the street image, like the Times Square kind of image, is in the background, and the floor is also right rainy because of the rain sound in the audio clip. And finally, I can say do the more complex thing of generating the whole video and audio. So here you will see that now everything is more dynamic. The street sound, the street is still the same, like Times Square in the background, but there's a more dynamic, right, teddy bear on the skateboard action happening. But the best part is you'll hear three sounds being generated now, right? Not just the rain from the audio clip, but the street noise from the image and the skateboard clicking, right, from the teddy bear text on the skateboard part. So this is sort of the whole notion of now any to any generation, right, is a very sort of popular concept in the community. The basic sort of details here of the method that I'll go into is that it has three stages: composable conditioning, joint generation, and inference. So in the first stage, which is composable conditioning, we train the LDM, right, the latent diffusion model for each modality. And the best part is they can be first trained independently, right, to ensure high quality generation for each modality. And then if you want to do conditional generation, right, from the left hand side, for example, audio plus language to image, right? What we'll do is the input modalities are then projected into a shared feature space such that any output LDM, in this case, the image one, can basically do attention on the combination of the input features on this shared space, right? So this allows you to have any combination on the input side without directly training for such settings. And then on the stage two side, it's the same thing, but on the output side, where we first add a cross attention module to each LDM. And then in this case, we also have an environment encoder, which allows you to project these LDM latent variables into a shared mixed space, right? So this allows you to create a mixed output space, right, for any unseen group of output modalities without having to train on these combinations. And all of this can now be done with linear number of training objectives. I'll show you a few more examples, like say audio plus image, right? Piano sound plus forest image, and ask it to generate text plus image. Or I can do something like text plus image to generate a video, right? And then what I can complain next about Cody 1 is that this is not how humans, right, do any to any generation. I will not say text plus image, give me a video, right? I want to be able to have an interactive, multi-step, natural, right, interaction with my Cody sort of any to any setup. So this is what we did in Cody 2, which was a spotlight last year at CVPR, which is in context, interleaved, and interactive any to any generation. So the idea here is that I can start with my sort of favorite, maybe right, input images like my pet dog, and also ask the model to generate the same concept, but with some of these art, right, sort of garden and arch images. And then I can say, hey, now can you take this rain audio clip and edit my image and make it more rainy and misty? I can even ask you to do reasoning like A minus B plus C, right? What's the edit between X and Y? And can you apply that same subtraction, right, to the new image that I'm working with? So it will also tell you the effect of the change, right? I changed the season of the scene. So this A minus B, it knows is like the change in the fall color seasons. It'll apply that same thing to your working image and tell you the change here. So Cody 2, I can again point you to the paper, but it has a lot of diverse capabilities, like I said, A minus B plus C, not just on images, but audio clips, street plus terrain minus street plus terrain, right? It's terrain plus rain. It can also do visual reasoning, like given A, B, and C, what happens next, right? It can do multimodal generation with reasoning, right? Given these frames, what happens next? Subject-driven video generation, also composition, right? A on B. So I'll not go into too much of the details here, but this is sort of right the more newer version of how Cody right should be interacted with. And then one of the last examples I'll give is now we still want to do any to any, but in this case, this is a more challenging problem of can we do any control to any diffusion backbone, right? So this is control adapter, which was an oral this year at iClear called efficient and versatile adaptation of any control to any diffusion backbone, right? So the motivation here is that control nets, as you all know, right, are widely used for adding spatial control to text to image diffusion models. And these can be done with different user conditions, right? Like depth maps, scribbling, and sketches from the user or human poses. But the problem is that when it comes to controllable video generation, these control nets cannot be directly integrated into new backbones, right? Because there's feature space mismatches. So these control nets, right, become for new backbones, right, can be a significant new burden. And the other problem is that if you start trying to apply image control nets to every frame in the video independently, then obviously you lose a lot of the temporal consistency, right? And all these other issues that come with videos. So that's the main goal of control adapter, where we basically design a lightweight control net adapter that can utilize these pre-trained image control nets, but be able to then do efficient and effective controllable generation for any new image or video backbone. And then the best part is while maintaining right temporal consistency across frames. So very briefly, I'll just describe the method here that we start with a pre-trained image or video diffusion model backbone, right? For example, this on the green left side. And then we also start with the blue pre-trained image control net. And then we insert these yellow control net adapter blocks, right? Between each block of the pre-trained image or video diffusion model and the control net, right? Corresponding block in the diffusion model versus the control net. And these control net adapter blocks consist of a series of spatial and temporal convolution and attention layers here. So the best part, like I said here, is that if you look at the red dashed arrows, then the gradients are backpropagated from the final output latent only till the control adapter blocks, right? They stop here. And this allows us to do very efficient training, right, while calculating gradients only for a very small part of the model. So here is some qualitative visualizations for the training efficiency, right, where you can see that if you use something like PixArt as an example here, right, control adapter trained on PixArt backbone converges much faster, right, in 300 time steps, 300 steps, 3 minutes, right, versus 2000 steps, while already achieving much better control style and output quality. And then more quantitatively, you will see that if we measure things like optical flow error and SSIM scores for spatial and motion control quality, compared to things like SDXL trained on 700 GPU hours, control adapter can get much better or equal spatial and motion control, but only with 10 800 GPU hours. And then the last important part is that we also innovated on multi-control conditions here, right? Where if you are given several different controls to make a much better video, right, without having errors with only one user control and also handling, right, synergy between the different controls. We first showed that if you use a mixture of experts kind of approach, then simpler approaches like unconditional global weights or even patch level MLP weights does not work. So we had to come up with this new approach called patch level Q-former weights to make multi-condition mixture of experts work. And here is a quick example where if you basically have four types of input conditions like depth map, human pose, canny edge, and segmentation mask, if you only generate videos based on one of these conditions, you will start seeing a lot of artifacts like the building could be blurred, or if you just use depth map and human pose, then the purse color might change, right? But if you use our mixture of experts approach with patch level Q-former weights, right, and then you're able to get a much better output video that satisfies all these input conditions. And then the last part of the talk is this quick example very recently from a few weeks ago where we tried to also extend this to 3D camera control. We call this EPIC. where the idea is to support both precise image to video and video to video camera control with complex 3D trajectories. And again, the focus is to be able to do this in very efficient ways. For example, only 2 hours on eight H100 GPUs. So this could be like a corgi video with different 3D trajectories, or another dog, right? But all these different parts of the video are showing you different trajectories. Or you could take one single trajectory and show it on different videos, right? So for example, if you see the friends example here versus this one below it, and it can also do image to video camera control. So the top part is the image, and then you give it a complex 3D trajectory and be able to, right, generate a video with that 3D trajectory. And again, very briefly, there's a bigger, more detailed method figure in the paper, but at a high level, the difference between previous work and our work is that previous work estimates the 3D point cloud at the top of the figure, right, using depth estimation and using the first frame, right? It renders these anchor videos with annotated camera trajectories, but these suffer from region misalignment due to point cloud estimation errors, and it's also limited to only camera pose annotated data. Whereas our method is creating the anchor videos doing based on this first frame pixel tracking. So you can see that we take the first frame here and do this pixel tracking. And this allows us to not only get accurate geometric alignment, you can see the red versus green, right, differences, the alignment errors here versus corrected here, but it also allows us to not depend on just camera pose annotated data. It can handle much more diverse data. And also, like I said, only 2 hours of 8 H100 GPU training. So I'll skip some of this. Crema is basically a multimodal approach for, I mean, I couldn't cover a lot of the long video reasoning work today due to the short time slot. But this is one example of being able to do multimodal composition for touch map, heat maps, optical flow, and so on, without having clashes between the modalities and through very efficient QLoRa adapters into video reasoning. And then you can check out this CVPR paper in the conference called Video Tree, where we can do hierarchical planning of which parts of the video should get more zoomed in information versus zoomed out, right, information for less important parts. So let me conclude briefly with some of the big challenges and research directions. In my opinion, I think we already discussed a lot about this sort of interesting debate, right, and trade-off between monolithic pre-training versus more planning and modular and, right, a mixture of experts kind of approaches, right, which do have some of these trade-offs, right, of a faithfulness, efficiency, right, human in the loop control, and so on. I would also love to chat offline about other modalities and properties, for example, gesture and gaze that we're using a lot for education-based multimodal models, as well as all the way to things like physics and 4D. We also do a lot of work on long distance video understanding, which I think a lot of the other exciting talks in the workshop also covered. And to me, there's a big sort of notion here to study on whether a lot of these models are taking shortcuts. Both the data sets are a problem, right, as we heard today, as well as models. So I think causality based counterfactual, right, evaluation and fine grained evaluation is a big key here, right, to make sure that models are actually understanding, right, as opposed to just taking shortcuts. On that note, like I said, out of domain generalization capability tests are extremely important, right? Most of these models are memorizing patterns in the data. So there's still not enough focus on unseen capability testing. And the last thing I'll say here is this is something that I cut out from the talk, but I'm very interested currently, and this is a big sort of topic in the community right now, on what is true self-improvement of models. Can we basically find issues and weaknesses of the model, right, and be able to generate data specifically for those weaknesses? But it comes with this important aspect of skill learning, right? You first need to understand what are the skills of the model, which ones are weak, and what's the right way to generate data. Yeah, so I'll end there. I already covered a lot of things about efficiency, right, in most of the work. Yeah, thank you. Yeah, and we are hiring students, postdocs, and faculty at UNC, so feel free to reach out.
Uh, Thank you, Professor Bansal, for